All right, so we were trying to prove this lemma, which says that if we have an operator on a finite dimensional vector space, and if it has an eigenspace of dimension k for some eigenvalue lambda, then the characteristic polynomial is divisible by x minus lambda to the power k. To prove this, we just recall the following property or identity. If we apply P to a set of basis vectors like this and take the wedge product, then this wedge product is just determined T times the wedge of this basis elements. And we are just applying this to the following basis vectors. The first k of the basis will be just eigen vectors. So it's a basis for the subspace, and then we just extend it to a basis for D. And then we just apply this operator, determinant of this gives a characteristic polynomial to this one. And by this, you know, instead of T, I have x minus identity minus T. So I will have x minus identity T, x minus identity T, x minus identity, no, x times identity minus T. So I just have that x times identity minus T applied to E1, E2, Ek, and up to En. And since this is an eigenvector, I can write it this way. This is due up to k, and after k, I have only these gadgets. So what we have is that determinant of x times identity minus T. And then this gadget is just here. You see, this is just x minus identity, right? Instead of this, I can write this x minus identity times the vector E1, and then x minus identity, not identity, x minus lambda times E2, which x minus lambda Ek, right? And then I have these gadgets. And x minus lambda is just a scalar. I can just take this outside. So what I will have x minus lambda, and how many of them? I have k of them, right? I have k many. Therefore, I have x minus lambda to the power k, E1, Ek, and then here I have x minus Ek plus 1 times Ek plus 1, which up to x minus t and minus t in n. Of course, you know, here I will have some polynomial times this wedge product. On this side, I'll have something like that. Right? If you open these things up, right, these are just, this is a combination of the basis vectors. If you just write that combination here and multiply this out, what you will get something like this. Some other stuff here, whatever the thing is, it will be, of course, a polynomial times E1 wedge Ek, and then Ek plus 1 after En. You will have something like this. Yani şunları da açıp çarparsanız hani her birisi E1'den E'ne kadar vektörlerin skalerlerle çarpımı linear combination olacak. Bütün bu çarpma işlemlerini yaparsanız sonuçta şöyle bir şey. Bir de buradaki çarpanlardan gelen bir polinomial. But you see, I have here E1 up to En. Here I have E1 up to En. And we know that this is a non-zero wedge product. Therefore, this coefficient must be the same. Therefore, this implies determinant of x minus identity minus t is just x minus lambda to the power k times g of x. Therefore, this polynomial just divides the characteristic polynomial. Tamam mı? Yani burada el-kol sallıyormuşum gibi gözüküyor ama değil. Yani şunu da açtığımızda bunun bir ifadesi var. Yani işte bir sayı çarpı E1, başka bir sayı çarpı E2, başka bir sayı çarpı E3 değil mi? Skalarlarla çarpacaksınız. Onu bunlarla çarptığınız zaman zaten E1'den EK'ya kadar olan kısmı gidecek. Geriye EK artı 1 ve yukarısındaki terimler olacak. Onların bütün çarpımından da sonuçta şöyle şu ifade gelecek ama tabii ki bir takım ekstra çarpanlar olacak. O ekstra çarpanlarda Gx diye bir şey olacak.
Gx şey mi oluyor? X üstü n eksi k eksi 1 şey.
Şu mu?
Aha.
Bilmiyorum. Yani sonuçta şey olacak. Tabii ki o. Yani karakteristik polinomun x eksi minus lambda üzeri k'ya bölümünden kendine çıkıyor.
K'dan sonra her bir şeyimiz basis elemanlar x eksi t ile çarpıyor.
Evet.
Sonuç olarak onların da o arada x olarak yazmamız galiba. Kaç ne yapmışlar?
Yani şöyle mesela t üzeri k artı 1 nasıl bir şey olacak? Atıyorum. Bu değil mi? A1, A1 artı A2, E2 değil mi? A üzeri n diye bir şey olacak. Bunu buraya yazacağım. Bir de bu var. Sonra bunlarla çarpınca zaten şu bir tanesi gidecek. Geriye kalanları kalacak. Yani oradan bir ifade gelecek. Ama dikkat ederseniz hani bir x var. Ondan sonra da bir takım skalerler var. Dolayısıyla bunların çarpımından bir şu terim gelecek. Bir de bir katsayı olarak da bir polinomial. So this finishes the proof. But this actually gives us what? This gives us the following. As a corollary of this, so this finishes the proof. As a corollary of this corollary, suppose think from E to D, that is isomorphic to E to the power n is diagonalizable. Suppose that lambda 1 up to lambda r distinct eigen values of t. O zaman bunların her birisine karşılık eigen space'lerim olacak, değil mi? W1, W lambda 1, W lambda r eigen spaces. I know that then the thing is the following. Şöyle bir şey yapmıştık. Okay. Buradaki all right. So if beta 1, beta r are some basis for W1 up to WR respectively. Then beta, which is W1, WR. So if I have this eigenspaces, okay, eigenspaces, then and if these are bases for this eigenspaces, then the union of this basis gives me a basis for the basis for B, and what else? The characteristic polynomial, the determinant of x minus identity minus 2 is just the following. It is the product of the following factors: x minus lambda 1 to the power R1, x minus lambda 2 to the power R2, up to x minus lambda, pardon. Onların dimensionlarının olduğunu söylemiştim. Bunlara K1, K2, özür dilerim. K1, K2, lambda R, K R. Burada K I dediğim şey dimension of lambda. So if our operator is diagonalizable, then we have a basis consisting of eigenvectors, and that basis is actually obtained as follows. For each eigenvalue, you consider the eigenspace, you pick up a basis for this, and then you just put those bases together. The union is a basis for the vector space, and also the characteristic polynomial has this form: x minus lambda 1 to the power K1. K1 is the dimension of the eigenspace corresponding to the eigenvalue lambda 1 times x minus lambda 2 to the power K2. That K2 is the dimension of the eigenspace corresponding to the eigenvalue lambda 2, and so on. Okay. And let's see why this is true. First, let's see why this is a basis. Okay, so beta 1, beta 2, beta R, and this beta 1 is a basis for W1, right? W lambda 1, so it has basis V1. Diyelim ki buradaki vektörler şey oldu. Evet, şimdi eigenvalue hangi eigenvalue'ye karşılık geliyorsa, lambda 1'e karşılık geliyorsa onunla şey yapmamız lazım. Lambda 1'in nedir? Nereye kadar olacak? Lambda 1 K1 tane var, değil mi? Aynı şekilde bir lambda R, beta R. Burada da this is for the eigenvalue lambda R, and here I have V1 up to the number n. How many? K and m. K R lambda R, bu R, and A tane eigen space'im var. İlk önce ne iddia ediyoruz? Bunlar şeydir, linear independent. Neden? Tek en linear combination of the form. Diyelim ki şöyle bir linear combination var. Bütün bunları işte çarpıp topluyorum. C bir lambda bir lambda bir C lambda bir sabit lambda bir sabit nereye kadar? Evet burada C lambda R 1 B lambda R 1 up to C lambda R K R B lambda R K R equals 0. Yani bütün bu vektörleri bir linear combination aldık, sıfıra eşitledik. Ne göstermem lazım? We must show that all these coefficients, this one, right? All these coefficients must be 0. Well, why this is true? It is because of the following. You see, this thing is a vector in this eigenspace, right? The second term is an eigenvector in the second vector space, and so on. And the last one, this one, is an eigenvector in this eigenspace. So, all these vectors, this one, next one, and so on, up to R1, right? I have R many vectors. This is the first one, second one, and so on. These are eigenvectors belonging to different eigenvalues. And a combination of them is equal to 0. But we know the following. Eigenvectors from different eigenspaces form a linear independent set. Bunu ispat etmiştik, değil mi? Farklı eigen value'lara ait vektörler alırsanız onlar lineer bağımsız. Bunu tek bir vektör olarak görüyorum. Bu vektörü aldım, ikinciye ekledim, üçüncüye ekledim, R'ye ekledim. Her birisi farklı bir eigen value'dan geliyor. Bunların toplamı 0. Yani ne demek? Bunlar lineer bağımlı. Ama bu doğru değil. Değil mi? Lineer bağımlı olamazlar. Ne zaman lineer bağımlı olurlar? Hepsi 0. So, since they belong to different eigenspaces, such a linear combination exists only if all of them are actually the 0 vector. So this implies that this is 0 vector, this is 0. But then, you know, this thing is a base. So this linear combination is equal to 0, means all these coefficients are 0. And this is the basis, and this thing is equal to 0, therefore all these coefficients are 0. Therefore, you see that all this C lambda I J's are 0 for all items. But this means that data is linearly independent. Tamam mı? Peki bu vektör üzerinde niye süperler? Why is the spanning set for the vector space, and basis olması için for this thing to be a basis, it has to be linearly independent, plus it should be a spanning set. But it is a spanning set because it's a operator is diagonalizable. Therefore, every vector is a combination of eigenvectors. Okay. Beta is a steady set since thing is diagonalizable. And that it has a basis for system of eigenvectors. Ama zaten bütün eigenvektörler bunların bir kombinasyonu. Dolayısıyla da bu base oluyor. O halde ilk kısmını yapmış olduk. Ne dedik? So this is the basis for B. What about the second statement? So we prove the following. If we have basis for these eigenspaces, then the union of those bases is a basis for the vector space. Then the second part is that characteristic polynomial can be written like this. But this is also easy by the previous proposition, because I know that the multiplicity of lambda 1 is k. In other words, I have k many linearly independent eigenvectors for the eigenvalue lambda 1. Therefore, this gadget divides this function, I mean polynomial. Tabii buradan şunu da söylüyoruz. Belki şöyle diyeyim. Yok. But since this is a base, so the union of these sets is a basis for B. And which is dimension of B is just the sum of the dimensions, right? So dimension of this one is just K1 because I have K1 vectors and then K2, and so this is just K1 plus K2, K1. The sum of dimensions of eigenspace, dimension of W lambda 1, dimension of W lambda K lambda. Now, by the previous proposition, x minus lambda 1 to the power of K1 divides f of x, the characteristic polynomial. X minus lambda 2 K2 divides f of x. X minus lambda r Kr divides f of x. But lambda 1, lambda 2, lambda r are all different, right? Lambda r is different than lambda j, if r is different than j. So if these polynomials all divide f, then their product divides f. So I have this. So, determinant of x minus identity minus t or c, whatever, f of x is divisible by this product is divisible by x minus lambda 1 to the power of r1, x minus lambda 2 to the power of r2, x minus lambda n r1 değil that, k1, k2, KR. Now, this is a polynomial of degree n, right? Degree of f of x is just n. What about degree of this one? Now, this has also degree K1 up K2, Kn, but this is just K and Kr, but this is equal to n. And they are both monic polynomials, right? This is monic, the highest order term x to the power n. And this is also a monic polynomial. Two monic polynomials both have degree n, and one of them divides the other one. This is possible only if they are equal. Hence, f of x is just equal to this gadget, x minus lambda 1 to the power k1, x minus lambda r to the power k5. Tamam mı? Yani eğer so if our operator is diagonalizable, then characteristic polynomial has this form. It's a product of linear terms. This lambda 1, lambda 2, lambda r are the distinct eigenvalues, and these exponents are the dimensions of the eigenspaces. Okay, so that's the conclusion. So from the characteristic polynomial, we can guess what the dimension of the eigenspace. If it is diagonalizable, then these are the dimensions of the eigenspaces. But of course, the dimension of the eigenspace need not to be this gadget. It can be smaller because not every operator is diagonalizable. It means that you may not form a basis consisting of eigenvectors. In that case, dimensions will be less than these gadgets. Okay? And in that case, your operator will not be diagonalizable. Let's do two examples.
Hocam, can you repeat the last part?
Hangisinin şeyi mi? Bu eigenvalue'ların
Yes, hocam.
dimensionlarıyla şey. Okay. Okay, now if it is diagonalizable, then your characteristic polynomial has this form, and these are the dimensions of the eigenspaces. In general, dimensions of the eigenspaces are smaller than these numbers. If they are not equal to these numbers, then it means that your operator is not diagonalizable. Yani elinizde yeterince eigenvektör yok demektir. Diagonalizable ise eigenspace'lerin dimensionları bu sayılar olacak. K1, K2, Kn. Ama bu sayıda vektör bulamayabilirsiniz. O zaman ne demek? O sizin operatörünüz aslında diagonalizable değil. Yani o karakteristik polinomdaki bu eksponentler sizin eigenspace'lerinize ulaşabileceği en yüksek boyut. Bu boyutlara ulaşıyorsanız diagonalizable. Ama ulaşamayabilirsiniz. Şimdi örnek göstereceğim. O durumda operatörünüz diagonalizable değil.
Okay, hocam.
Hocam, can we say that our minimal polynomial has the same form, but with different powers?
Yes, I'll come to that. Actually, minimal polynomial will determine exactly when the operator is diagonalizable.
Okay.
From the characteristic polynomial, we cannot say that it is diagonalizable or not. But from the minimal polynomial, you can say it right away. Okay, let me just consider again the same example. Aslında bir dakika. Bakayım şurada bir şey size verdiğim exercise sheet'te de olabilir. Examples değil. Evet. Bir tanesi şu olsun. Okay. A şu matris. Yani isterseniz bu matris veya operatör gibi görün. 0, 3, 0, 0, 0, 2. Bakalım bu diagonalizing is diagonalizing. Okay, now if I can find a basis for the vector space consisting of eigenvectors, then it is diagonalizable. So let's find eigenvalues and eigenvectors. To find the eigenvalues, I need to compute the characteristic polynomial. So f of x, which is determinant of x and identity minus n. So what is this? X minus 3 minus 1, 0, 0, x minus 3, 0, 0, 0, x minus 3. My matrices are very simple ones, so it's easy to compute this determinant. Nedir determinant? Bu üçgen bir matris olduğuna göre determinant direkt değil mi? Diagonallerin çarpımı. Yani x minus 3 squared x minus 2. So I have two eigenvalues. Lambda 1 is just 3 and lambda 2 is 2. The exponent K1 is just 2 and the exponent here 1, right? So for this to be diagonalizable, the eigenspace for this one should have dimension 2, and for this eigenvalue, the eigenspace should have dimension 1. Burada her zaman bir boyut olacak. Yani çünkü bu zaten eigenvalue demek. Bir tane eigenvektör vardır. Bir tane varsa o zaman boyut en az 1. Sıkıntı şurada çıkabilir. 2 tane lineer bağımsız eigenvektör bekliyoruz ama 2 tane olmayabilir. Ki bu matris öyle bir matris. Sıkıntılı. Neyse yapalım bakalım. Nasıl?
Geometrik power'la, yani geometrik şey sayısı kadar eigenvektör var.
Anladım. Evet. Yani o kadar vektör var mı gerçekten? Cebirsel olarak 2 tane olması lazım. Eğer gerçekten diagonalizable ise 2 tane bulacağız. Bakalım şimdi var mıdır? So, for this eigenvalue, let's see what is the eigenspace. So, eigenspace means what? Eigenvector is A times B should be just lambda 1 times B, right? So it should be just 3 times B. And this means A minus 3 times identity B is 0. So it is a solution of this system. So from A, I subtract 3 times identity. If you do that, A is this vector, not vector. A is this matrix. If you subtract 3 times identity, you get 0, 0, minus 1. So let's see what we get. 0, 1, minus 1, 0, 0, 0, 0, 0, 0, minus 1.
A'dan bir tane şey çıkartıyor.
A'dan çıkartıyoruz. Ha, ters yap. Ha, tamam. Bu evet. A'dan çıkarttığımız şu artı 1.
Alttaki eksi.
Tamam. Şimdi V ile çarpıyorum 0 olacakmış. V vektörü ne olsun? A, B, C olsun değil mi? 0, 0, 0. Çarptığınız ne çıktı? B eşittir 0. Bir de eksi C eşittir 0. Bu ne demek? B ve C 0'mış. A ne isterseniz o. Değil mi? So what is the solution space? So B is just A, 0, 0, right? So it is just A times 1, 0, 0. Well, it means any eigenvector is a multiple of this one. So I have only one eigenvector, basically. So my W lambda 1, which is W3, the eigenspace corresponding to the eigenvalue has dimension 1. So it is just spanned by this vector. 1, 0, 0. 1, 0, 0. Therefore, my operator cannot be diagonalized, right? It is not diagonalizable. This implies that A is not diagonalizable. But let's find W2 also. So, just for the sake of completeness, number 2 is 2. K1, no, K2 was 1, right? Again, I mean, the exponent of x minus 2 was 1. Bakalım, işte burada ne olacak? A minus, no, A times B should be just lambda 2 times B, which is just 2 times B. Therefore, A minus 2 times identity, B is equal to 0. So, we have to solve the following equation. Size gönderdiğim notlarda bu örnekler yok. Hani daha özet şeklinde. So A minus 2 times identity B. A was this matrix. 2 times identity çıkartırsam 1, 1, 0, 0, 1, 0, 0, 0, 0. Times B, let me say again ABC. Okay, it is 0, 0, 0. From this we get 1. A plus B is equal to 0, and B is equal to 0. Well, this implies both A and B are equal to 0. C is arbitrary, so my vector has this form. A is 0, B is 0. C is arbitrary, so 0, 0, 1. So therefore, W number 2 is W2. The eigenspace corresponding to the eigenvalue 1 has dimension 1 as expected. And this is the eigenvector. Okay? Ve dikkat ederseniz eigenspace. So this is one vector. This one is one vector. If you put these two bases together, you don't get a basis for R3 because you have only two vectors. For the operator to be diagonalizable, you need 3 vectors, right? So that's compatible with the statement that this operator is not diagonalizable because it doesn't have enough eigenvectors. Tamam mı? Şimdi bir de başka bir örnek yapalım. Okay, let's see another example. O da şu olsun. So let's say B is this matrix 3, 0, 0. Evet. Birbirine bayağı benziyor değil mi? If you compare with A, it's almost the same. Instead of 1 here, we have here, right? Now, what is the characteristic polynomial? Determinant of x minus identity minus b. So this is just the determinant of x minus identity minus b. So x minus 2, 0, 0, 0, x minus 2, minus 1, 0, 0, x minus 2. Well, the characteristic polynomial is the same. X minus 3 squared x minus 2. Right? It is the same. Number one is 3. K1 is 2. Number 2 is 2 and K2 is 1. Now let's find the eigenvalues, eigenspaces. So for this eigenspace, well, we consider the following equation. B times an eigenvector is just number 1 times the eigenvector, so it's 3 times E. So B minus 3 times identity, B is 0. Bakalım orada ne çıkacak? So this is B. I subtract 3 times identity, so we get 0, 0, 0, 0, 0, 1, 0, 0, minus 1. And then here we have A, B, C equals 0, 0, 0. Well, we get what? B is 0 and minus B is 0. Well, they are the same equation. So C is 0. A and B are arbitrary. So any eigenvector values 4. A is here, B is here, but C has to be 0. Değil mi? Onu da bize 2 kere söyledi. Bir kere laftan anlamayız diye. Okay. So what is this now? A basis for this. This is A times 1, 0, 0 plus B times 0, 1, 0. So a basis for the eigenspace W3. So basis for this 1, 0, 0. 1, 0, 0 and 0, 1, 0. Buna B3 mi demiştik? Ne demiştik? 3'e karşılık gelen eigenspace. Nasıl göstermiştik? Onun notasyonu neydi? Unuttum. Beta 1 demiştik ya. Lambda 1'e karşılık gelen eigenspace. Peki. Diğer eigenspace nedir? Buradan bu sefer diagonalizable çıkacak. Çünkü 2 tane vektör bulduk. Öbüründen de en az bir tane gelecek. Fazla da gelemez. Dolayısıyla 3 tane vektör öncelikli olacak. So, what about the eigenspace? Number 2, which is 2. So, B is just number 2 times 3, which is just 2 times 3. So B minus 2 times identity is 0. B minus 2 times identity, so 1, 0, 0, 0, 1, 1, 0, 0, 0. And B is just, let's say, C equals 0, 0, 0. So from this we get A is 0, B plus C is 0, and that's it, right? So things the following point. A is 0, B and C are just inverses of each other. So if this is B, then this is just minus B, right? Because B plus C is 0. So this implies this is just 2 times 0, 1, minus C. So this is my third eigenvector. So beta 2 has one element as a vector, and this I can just take this vector. And now I know that this thing, right? I just take this basis and the other basis, put them together, I will get the basis for the vector space. So 1, 0, 0, 0, 1, 0, and 0, 1, minus 1 is the basis for system of eigenvectors for V. Therefore, hence T is well, not T, but B is universal. Regularizing olduğunda nasıl hani bunu şey olarak yaparsak bu bazı kullanarak baz değiştirme matrisini yapmamız lazım değil mi? Diyelim ki beta tilde şu olsun, bu standart basis A1, 1, 0, 0.
Hocam kamera.
Kamera, pardon. A2, 0, 1, 0. 0, 0, 1. I want to write the operator in this basis. So, B in this basis, beta to beta, is what? It is just B in the basis beta tilde to beta tilde, and here I will write identity from beta to beta tilde and beta tilde to beta. If this is the operator T, well, beta tilde is just the standard basis, and this is just B in this basis is just the matrix B, and this is just P inverse, because here I have beta to beta tilde, and here we have beta tilde to beta. It is just inverse map. What about this one? Bu nedir? B'nin bu bazdaki matris gösterimi ne olacak? Yani şimdi benzer şuydu, değil mi? 3 tane eigenvektör. So V1, V2, V3. V1 is just 3V1. V2 is just 3V2. And V3 is just 2V3. Therefore, this is just 3 times V1, 3, 0, 0, 0, and this is 0, 3, 0, and 0, 0, 3. And what is this P? P is just the identity operator written in this basis. Yani P matrisi nedir? Identity'nin beta'daki beta base'indeki görüntülerini beta prime'da yazacağım. Şimdi identity B1, bu B1 neydi? 1, 0, 0. Değil mi? Yani bu zaten E1. A'lar tipi B2. O da B2. O da zaten E2. A'lar tipi B3. B3 ama B3 nedir? Pardon, E2 eksi E3. So this matrix P is then what? So P is this. E1 has image E1. So in this basis, E1, E2, E3, this has coordinates 1, 0, 0. So 1, 0, 0. And then the second one is this, and the third one is just 0, 1, minus 1. So P is just this matrix. Okay. Evet. Gelecek derste ne yapacağımı söyleyeyim. Next time we will prove the following theorem. P is diagonalizable. So we will characterize when P is diagonalizable. If and only if the minimum polynomial Dn x is a product of distinct linear factors. Bu A matrisi için D2'yu hesaplarsanız D2 şey çıkacak. X eksi 3'ün karesi X eksi 2. A için. B için D2 değil, D3 özür dilerim. Üçüncü şey bu ise şey çıkacak. D X eksi 3, X eksi 2. So this is a product of distinct linear factors, but this is not, right? It has x minus 3 squared. Therefore, A is not diagonalizable, but B is diagonalizable. So next time we will prove this. Sonra da Jordan formu yapacağız. Önümüzde karakteristik, pardon, canonical formlar bitmiş oldu.
Hocam B'de de x eksi 3'ün karesi dememiş miydik?
D3'te olmayacak. Karakteristik polinom öyle de minimum polinomlar farklı.
Tamam.
Yani ikisinin de karakteristik polinomu bu. Şu polinom. Ama minimum polinomlara geldiğimiz zaman A'nın minimum polinomu karakteristik polinomuna eşit çıkacak ama B'ninki farklı çıkacak. Tamam mı?
Okuyor hocam.
Okay. Başka sorusu olan var mı? Any questions?
Hocam sonuncu söylediğinizin nedenini açıklayın.